streaming. Make sure that we are recording the voice. Yep. Okay, good. Alrighty, so I'm gonna get started here, even though half the class is not here yet.
They're lost. They're lost.
Well, I have to tell you my own experience of taking the equivalence of this class many years ago, as in 1986. Yeah, I'm old, I'm that old. So when I took this class, it was from San Francisco State University, which is not well known for computer science or engineering or anything like that. But they had a adjunct faculty who normally taught at UC Davis and UC Berkeley, but on Mondays, that guy would kind of moonlight and get a part-time job over at San Francisco State. So that class was a Monday-only class from 7 p.m. to 10 p.m.
Oh.
Yeah, and it's 3 hours of lecture. It's not like hour and a half of lecture plus hour and a half of lab, because back in those days, labs were just lab. You guys go to the lab, I do not. The professor did not go to the lab at all. It's just the students going to the lab, and we only count lecture hours for units. So the class was a 3-unit class because it met 3 hours per week. Okay. When we started, the class had 60 people. Halfway through the semester, only about 30. At the end of the semester, there were only like 12 people left. It's mostly because it was difficult to a certain point, but it also has to do with the resources to do homework assignment was very limited. We are talking about a class of 60 people to begin with, but there were only 4 hardwired terminals in the lab that could be used to do homework. In other words, at the very beginning, if you want to get your homework done, you have to make sure that you use only one of the 4 hardwired terminals in the lab to do your homework. So I usually get my homework done within the first 2 days of assignment, and there's usually no one in the lab at all. And most homework assignments had a due date of about 2 weeks, not 1, but 2. And most people would kind of wait until the last 2 or 3 days. So you can kind of imagine, what happens, on those 3 days. You have 59 people, 60 minus 1, right? 59 people trying to line up and use those 4 terminals to get the homework done. And they have an upper limit of how long you can stay with the terminal, like 2 hours or something like that. So after 2 hours, at that time you line up, and you go to the board and you add your name to the end of the queue, and then you wait until it's your turn again. Oh my God. Yep. So you guys have your own installation of Logisim, right? I mean, you have your own version of GCC. You can work on your own homework anytime you want to with your own PC, because you have laptop computers now. Not in those days. I can't even use my modem to dial in because those terminals were hardwired. You have to be in the lab physically to get it done. So the good old days.
Oh, that's hilarious.
There was no practical internet. I'm pretty sure ARPANET started to exist already, but for the rest of the people, there's no internet. You have BBS, you have bulletin board service, and that's about it. And those are only good for chatting. They're not good for looking for anything.
And MUDs?
Huh?
And MUDs?
And what?
MUDs?
Months?
Multi-user dungeons?
Oh yeah, they got those too. Yep, we got games from that era.
Did you ever learn Fortran?
Nope, I never learned Fortran. I only learned how difficult it might be. All right, so last time we talked about the syntax of a scientific notation in base 10. Are there any questions about this part? No questions? Are there any questions about how to understand this particular description? It is the regular expression description of a base 10 scientific notation. Yes, go ahead.
Can you use this equation to find for an example? For a sample example?
Can I use this to find?
Can you do a sample of using this?
Oh, absolutely. Well, but there's an infinite number of things that can be generated using this regular expression, so I can only go through a few, okay? So let's go ahead and take a look at a few of these examples. I'm going to use mousepad on the side so that we can keep the regular expression on screen while I work on, examples. One fits the description. Okay, so now how does it fit the description? It does not have the plus or minus to start with, but that's okay because that's optional. How do we know that's optional? Backslash equal to makes it optional. Okay. This part here is not, there's no quantifier after this one, which means we need exactly one of these, which is a single digit. And do we have a single digit? Yep. Okay, so if you switch back here, we have a single digit, which is 1. What about this part here? This entire thing is optional. In other words, I do not need to have a decimal point plus some other digits. That's okay. And I don't have those. And then you look at this entire thing, it is also optional. I do not need to use the E plus blah, blah, blah. So that's entirely optional as well. So that means 1 by itself is going to fit this description. Okay? You can have -2 E plus 2, 3. That will fit the description too, because the leading minus is optional, but it fits that. Okay, I have that one optional sign. It's cool. The 2 is going to fit the first backslash D, the first digit. Okay, so it's okay. But then the point blah 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 is optional. It is missing in the second number, but that's okay because it is optional. It's okay to be missing that. Yep.
Backslash D
is a digit. Is a base 10 digit.
So this is period base. I don't understand.
The backslash period is just a period.
Yes,
because period by
character.
itself is a.
It's followed by backslash D.
Right.
Saying period and then character.
Asterisk means any number of the previous one. So the asterisk applies to backslash D, which means any number of base 10 digits.
Okay.
So it means, so basically the bottom line is the quantifiers, which in this case would be the backslash equal, the asterisk, and also the backslash plus. These are quantifiers. And all the quantifiers apply to the thing that is immediately before the quantifier itself. So if it is a backslash D immediately before the quantifier applies to the digits. On the other hand, if you have backslash open paren and backslash close paren immediately before the quantifier, then it applies to everything that is enclosed in that entire group. Is that okay? All right? Okay. So just to give you a few more examples, okay, we can have 2.34. That's a scientific notation because it is missing the exponent part and it has the optional .34, the period 34 part. So that's okay. 2.34 E is not good because once you have the E, you have to have at least one base 10 digit after that. Because you can see the E is followed by an optional sign, so that part is optional. Then you have a single backslash D with a backslash plus. The backslash plus is basically saying whatever is immediately before the backslash plus has to occur at least once. Okay, so that means this is not okay. 2.34 E is not okay. I have to give it something after that. Okay, now it is okay. Are we doing okay so far with this? Okay, it's good. I believe so, but it's always good to check. It is recording and the voice is active, so we are recording correctly. All right. Any questions about the base 10 scientific notation? It is all explained, okay? I'm just verbally explaining things that are already kind of written in the notes.
Can we ask you about homework?
Yep. Okay, so the homework, if I read forward a little bit here, okay? So I want to break up a scientific notation into its components, okay? So in this case, if this is the actual input, then the overall sign of the number is negative. So the sign bit is a 1, okay? To remember that this is a negative number. The mantissa is 2.67. The mantissa is basically the number other than the exponent. So that's the mantissa. It is 2.67 in this case. And I call this M10 because it's the base 10 mantissa. That's why there's a subscript of 10. And the exponent is also the power of 10. In this case, it's -6. So E10, or the exponent of 10, is -6. The value that is represented in this case is this thing. If the sign is true, then we use -1. If the sign is false, we use 1. In other words, we either choose -1 or 1 to multiply to the rest, to control the sign of the number itself. Is that okay? M10 is called the mantissa. It is specifying the, not the magnitude of the number, it is specifying the, I don't know exactly how to describe the mantissa, but it's describing the value part of the number, okay? And then the exponent is controlling the order of magnitude of that number. Okay, so are there any questions about this formula, which is representing the value once we break it up into all of these components? Because that's the first part that you need to use for your homework. Yep.
What's the question mark in the colon have to do with?
It's a ternary operator.
And if that is
If
then
it's
what?
then otherwise.
Yep.
If this is true, do this. If not, what?
Yep. We have seen that already when we talked about signed numbers. So basically it's an if then else, but collapsing all of those into a single expression. It's quite useful. You know, it seems really odd and really weird to begin with, but once you get used to it, it is actually quite useful. Okay. All right. So, as an exercise, which is actually your homework assignment, I want you to write a parser. So let's switch to the homework assignment itself and look at the description of the homework. So the first thing I want you to do is to download this particular file. I will explain that in just a moment. As a starting point, do this assignment in a single file and name that file in your last name followed by your first initial, which is the name of the file. So and then followed by .c. So this assignment is a C program, not C++. Okay. So technically speaking, no one should have a problem with this because C is a subset of C++. But I said technical because a lot of times when you are in a C++ class, sometimes they neglect to talk about some of the older features of C that is not commonly used. Okay, so but I don't think this homework assignment would involve much of that stuff. The program must be compilable using GCC. So for those people who want to use the Microsoft compiler to compile the program, it's okay. You just have to make sure that it is also compilable using GCC. You install GCC and try it out, or CodeBlocks. Okay.
Oh,
Yep.
okay.
I'm just curious, but what would be the incompatibilities between the two compilers?
They might have assumptions about whether certain header files are present or not. But how you end the program can be a little bit different. So this program doesn't need any special ending. Doesn't need a pause at the end. Okay, because I don't need that. I'll show you what parse sci.c, the template that you can use to begin with this program will look like. So once we have that, then it'll be kind of clear. Okay.
Question.
Yep.
Is GCC installed on the power server? Yes.
It is installed on the power server, but whenever you use CodeBlocks, it is using GCC already.
Oh, okay.
So any program that compiles in CodeBlocks is already going to work in GCC.
Do we have access as a result of this class? Do we have power server access?
No. Because you can, well, if you want to use a Linux tool to do the homework for this class, I can give you guys a virtual machine, a Linux virtual machine that has GCC installed in it. So that's okay. I kind of want to save the power server for the web classes. Because the web classes seldom have runaway processes where the program just keeps going and going and going.
It'll be totally fun.
Yep.
You're teaching PHP right now, right? You're teaching PHP.
Yes, I am. Yep. And sometimes they do have programs that goes on and on and on. But I think Apache does kill those processes by itself too. So, It's not as big of a deal. All right, so let's take a look at this file. Unfortunately, I did not move the link to this particular class, so I'm going to have to create a new link to get it done. So it's all coming from the other class, the Tuesday, Thursday class. And we'll take a look at modules. Yep. So we're going to leapfrog, a few times. Okay, parsi.c, and we will download it. It's a tiny little program, but really fun. Okay, download. There we go. And we'll download save file to the temp folder. Okay, fine. There we go. All right, so I'm going to go to my trusty Vim and take a look at parsi.c. This is the program that you're supposed to start with. I'm going to save a copy and link to it from your class, from this class, so that you guys have access to it too. But before I do that, I'm going to just kind of go over the code a little bit. And I'm going to enable line numbers so I can refer to the line numbers. We'll start with line 17 because that's the entry point of the entire program. ARGC and ARGV they are always there. Okay, the number of arguments and also the array of arguments themselves is always there for every single C and C++ program. It's just that most of the time in your homework assignments, you ignore that, okay, because we don't use it in most homework assignments. But it's always there. On line 19, I declare a local variable called p. It is of the type parser, okay? So parser is a structure defined up here. A struct in C is kind of like a class in C++, except everything is by default public. And you cannot have member functions in this case. You can only have members, but not member functions. So in this case, you can see that we have ptr being a const char pointer. Now, remember, this const applies to what pointer points to, ptr points to, but not the pointer itself, which means you can change the pointer to point to different locations, but you cannot change what the pointer points to, which is fine because we just need to parse a string into the value that is represented by a base 10 scientific notation. We are not here to make modifications to that string. Line 4 is saying sign as an integer. I use this int because there's no bool in regular C, so int is the usual way of representing something that's either true or false. Mantissa 10 is an unsigned because there's no need to represent negative values in this case. And exponent 10 is an integer, which means it can go positive or negative. Okay. And then when we get back here, if ARGC is greater than 1, do the following, otherwise there's nothing to do, because when we run this program, we want to run it with a base 10 scientific notation after the name of the command. And that is how we pass a string for the subroutine parse sci10 to process. Okay. So if ARGC is greater than 1, then I initialize the ptr member of p to point to the beginning of that string. In other words, this is all done for you. Don't modify main. Main is already done. You don't have to deal with main at all. But I'm just explaining how it works. So ptr is already initialized to point to the first const char of a string that is the text representation of a base 10 scientific notation number. Is that okay? So it's going to be character by character. Okay? And then I immediately call a subroutine called parse sci10, parse scientific notation in base 10, using the address of p as a argument. So when you look at this one, and the first line kind of tells you what you're supposed to do, is you have to write your code here. But I gave you 3 lines of code to begin with. So the 3 lines of code here from line 12 to line 14 are freebies. Thank you. Reasonable, initialization stuff. Okay, so no problem. Okay. So what you need to do here is to do what a parser is supposed to do. You're supposed to populate sign, mantissa 10, and exponent 10 of a parser structure based on the pointer PTR, or the string that is pointed to by PTR. Is that okay?
So you want us to make a new struct.
No, you're not making a new struct. You're modifying what p-parser is pointing to. And that's why p-parser is pointing to just a regular struct parser and not a const struct parser, because you're expected to change the members. Is that okay so far? Any questions? Yep.
So we're not modifying main at all, no input validation?
There's no, yeah, you can assume the input is correct. So I'm giving you a valid scientific notation to begin with. So there's no need for error checking. In real world, error checking is important, but it is usually done by regular expression. So anything that did not get through the regular expression that we talked about is already bad, and we just chuck those, okay? So typically, you don't have to worry about error checking at this point. You can assume the number is already properly formatted, following that convention described by the regular expression. Yep.
So just out of curiosity, what's line 25 supposed to be?
Line 25 is a label. Okay, so L1 is a label, and it is here so that I can use a script to grade your submission.
Interesting.
So I'm going to show you guys how the whole thing works, okay, as far as my workflow is concerned, so that this way, you guys know what not to do. Like, don't move L1 to some other place, okay? That would not be a good thing. Okay? Do not modify main, okay? Just leave main alone, okay? And just focus your code in parse sci10. You can make subroutines too, okay? And I'm strongly recommending people to make your own subroutine so that you can contain the logic of parsing each optional part of a scientific notation in its own function. That makes it easier to debug because the bugs will be self-contained within the function itself. So are we doing okay so far with this code here? Okay, I'm hoping that nobody feels that they're seeing something that they have not seen in C. Yep, go ahead.
So kind of just to recap, we can assume that anything that this parse sci10 function gets is going to be, it would fulfill that regular expression.
It conforms to it would conform to this description. So I would only give you a string that can get past this regular expression as the test string for you to parse. Okay. Good question. Any other questions? Okay, so I got two things to do. One is to upload it to Canvas first. Okay, so let's do that first. I can do it in two ways. I can just do it here. And I think Canvas is actually not that fast. I think there are some performance issue because I think Moodle is actually a bit faster than this, popping up the editor and stuff like that. Could be JavaScript on the client side. All right, so let's find the first reference to this. Okay, there we go. So we just click this and say, oh, it doesn't let me upload the file and link to it in one single step. Okay, I'm hoping I can have attachments to the homework assignment.
It's the link.
At the bottom?
The very, very bottom.
That file.
It's not. It's only adding who gets this homework assignment. I don't think it
At
can.
the very, very end.
Send the homework assignment to everyone.
Links, files, images.
Sorry?
If you go all the way down, I saw links, files, and images.
Ah, there we go. Okay, there we go. Thank you. So upload a new file. Parse.c and upload. Okay, so now the homework assignment is self-contained. The file is already here. Okay, so is the file still there? I mean, do I still have it uploaded? Yep, I do. So how do I create a link to it?
So what if
You can probably find it. Yeah, go ahead.
so you just, did you just delete it? Why don't you try just pasting over that one?
Did you cut it or did you?
Okay, but which button do I use here to link it here? Okay, can I click this? There we go. Okay,
And then just delete something.
get rid of this. There we go. I think that's it.
Oh.
Okay, so let's save the file, save the homework, and double check. Click this. And, well, we have to make sure it is the same thing, so we'll save it in a different name.
Just the same ones.
And then we'll double check. Okay, we'll div.
Assuming makes it, if it breaks, there's future.
Oh, they're both in temp. Div parsi.c, parsi2.c. They're the same. Okay, cool. Important to double check. Okay, so your program is to parse any input that is consistent with the regular expression in my nodes. The mantisas that I would use as test cases are guaranteed to fit in a 64-bit unsigned integer. And the best way to look at this is to look at the table here. Okay, so if the input string is -2, then I want sign to be anything other than 0, which is true, right? I want mantissa to be 2, and I want the exponent to be 0. Does that make any sense? The first row. Okay. Second row. If the input is 20, which is actually not, which is breaking the rules. Okay. If I give you 20, okay, let's skip this one because I'm not supposed to give you 20. Skip this one. Okay. Next one up. Okay. 2E1. Okay. So if the input is 2E1. Then I want the sign to be a 0 because it is not negative. I want the mantissa to be 2 and the exponent to be 1. Is that okay? All right. If I give you 2.000E3, now this is the fun part. Okay, I want the sign to be 0. Okay, that's cool. But the mantissa is now 2000. In other words, the mantissa that you're actually storing in the structure is kind of like the mantissa without the decimal point. Okay, it's the entire number without the decimal point. But that is going to change the actual value represented unless I do some trick with the exponent. And that's why you see the exponent here is 0, because every time I shift this decimal point to the right-hand side by 1, I'm decrementing the exponent of 10 by 1 to compensate. Does that make any sense? Because I need to preserve the value represented by the scientific notation. So the only way to shift that 0 from here to here so that I can get 2000, but preserve the value represented, is to say, oh, the original exponent of 10 is 3, but because every time I shift, I have to decrement 1, so we have 0 left. Yep.
So, we're not outputting anything, we're just pointing to, are you expecting basically the table, quote unquote?
No, this is just giving you, some test cases that you can play with. Yep.
What do you expect? Like we take in, what do we call it, a regular expression, or no, a number that fits in with the regular expression, and we
Correct.
We don't output anything?
You do not output anything.
We just point to a new string.
Right. So I'm going to show you how I'm going to test your code. Okay. All right. So the next one is this one here. Okay.
It's a char, right?
So when you look at this particular input, the sign is negative, which means the sign member has to be a non-zero value. And I just use non-zero here because there are tons of many options to choose from. Okay. So as long as it's non-zero, it's good. And then 201 is the mantissa because I'm getting rid of the decimal point here. But because every time I shift the decimal point, I have to decrement the exponent of 10, and I have to do it twice this time. So the original 10 to the power of -4 is now 10 to the power of -6. Is that part okay? Okay, all right. And then this one, The plus here the first plus doesn't do a single thing. The second plus really doesn't do a single thing. But because the regular expression specifies that that plus is optional, and so you have to accept it. You have to say, yeah, it's not important, but we'll take it. So 2 is the mantissa, and then in this case, 6 is the exponent of 10. So you put it here. Now the 2 zeros are interesting because the first 0 has all the zeros, okay, which seems to make sense. But then the second 0 is -0. As it turns out, the double floating point number representation does allow you to specify a -0. So you have to parse this one and say that the sign is non-zero, but the mantissa is all zeros, and then the exponent is 0 as well. Are we doing okay so far with this? Okay, all right, excellent. So let's go ahead and take a look at an example. I'm going to use my notepad here. And we'll just go, okay, let's take a look at minus 2.7 e minus 5. Okay, there we go. So it's a fairly simple example, but I'm just going through the logic of the program so that you can understand the pseudocode, or can try to come up with the pseudocode. All right, so when you look at this number, when you look at this input string, you know that what the value is. You can break out all the individual parts already. That's because we run on eyeball algorithms, which are untranslatable into C.
For now.
For now, yes. So what my recommendation is to look at things from the perspective of your program, which means you only see one character at a time, okay? So you see the first character, and you go like, okay, what am I expecting here? I'm expecting an optional sign, okay? It can be a plus, it can be a minus, it can be none of those, okay? If it's none of those, then I don't know whether the rest is right or not, but I know I don't have anything to do. Does that make any sense? Since minus is one of the expected character, so I would say, okay, we can see the sign of this number is negative, make sign non-zero, okay? And one more thing you have to do, move the pointer to the next character. Because every time you process a character, you recognize what it's for, you have to move on to the next one. When you move on to the next one, you know that you're done with the sign already. In other words, this is the beginning of the next logical unit to process just the digit before the decimal point. Okay? But what you will be seeing in your program when you scan the string pointer is not pointing to the value of 2 as an integer. It is pointing to the character which has the ASCII code of 2. So now you have to figure out a way to convert the ASCII code of 2 to the value of 2. Okay? Which is actually pretty easy, because you can look up the ASCII table and find out the ASCII code of the digits. The only thing you have to confirm is it's contiguous, which means the ASCII code of 1 is 1 more than the ASCII code of 0. The ASCII code of 2 is 1 more than the ASCII code of 1, and so on. Because as long as it is contiguous like that, you can use one simple math operator to do the conversion. I cannot imagine why any encoding would make this not contiguous. Okay, but ASCII is consistent. Huh?
It is, if I recall correctly.
Sorry?
It is, if I recall correctly.
It is contiguous. And in fact, in ASCII, even the letters are contiguous. So A to Z is one contiguous,
65
block.
through 89, I want to say. And
Well,
then
65 plus 25, right? Yeah. But in ABCDEC, they're not contiguous. And that's why we're not using ABCDEC. Okay, so you look at this 2 and you go like, yes, I am expecting a digit here because this is after the sign. I am expecting 1 digit. You process it, okay, and you store it into the mantissa. So you say, okay, the mantissa at this point is 2, okay, and once you move past this point, then you go to the optional logic and you ask, do we have any decimal point and additional digits to the right of the decimal point in this particular number? And then you see a period. that confirms that that section is present. Okay, so that will basically change the mode of what you interpret, how you interpret what is following, because now you know this 7 is after the decimal point. It belongs to as a part of the mantissa. But remember, I don't want to store 2.7 in mantissa 10. I want to store 27 in mantissa 10. But at the same time, you also have to remember to decrement exponent 10 by 1, because we are implicitly shifting the decimal point to the right by 1 place. So you got to do all of those things for each digit to the right of the decimal point.
The exponent
EXP10.
EXP10 is an int, right?
Is an int. Yep. So it's
You just add
fine.
a negative one to it.
Yes,
Okay.
it's fine. You can go negative. Yep.
Alright.
So once you process the 7, then you will have 27 stored as mantissa 10. You have some non-zero value for sign, and you will have -1 as EXP10.
Yeah.
Is that okay? And then you do this one, and then you parse this one. You are expecting this to be another digit because it's supposed to be a loop. Looking for digits. Like any number of digits after the decimal point. Except, hey, this is not a digit. So what do? You get out of the logic expecting more digits, and then you move on to the section of code that deals with the optional exponent. And then the first thing in the logic to deal with the optional exponent is to say, do we have an E? We do have an E. Good. Move the pointer. Okay? Remember, every time you recognize something, you have to move the pointer so that you can move on to the next one. Now you're onto the optional sign part of the exponent. Okay? It is optional, so you can say, so your program should be asking, is this a plus? Is this a minus? If so, I'm going to do something with the exponent. If not, we'll just assume the stated exponent to be 0. Okay? And this is saying that, okay, the exponent is negative. Fine. Okay? So you have to use a local variable in this case. The structure, there should be nothing in the structure to change at this point. You have to use a local variable to remember that the sign of the exponent is negative. Do not change the sign of the structure itself, because this is not the sign of the overall value. It is the sign of just the exponent. Okay? Then you say, okay, after the sign, which is optional, which I found, would be a bunch of digits, at least 1. Okay? So here's a digit, it's 5. Okay, cool. So you will convert the ASCII code of 5 to the value of 5. Okay? And you will keep doing this until the end. Then you apply the negation to the entire number that you have parsed. And then you apply the bias, you apply the adjustment that you have done earlier to that number. Okay? Okay, so let's say this is okay. Okay, we got a 5. So now you remember the exponent is negative, but at this point it is just 5. Okay, so those are the things that you use local variables to remember, not members of the structure, because we are not quite ready to store anything back to the structure yet. At the end is guaranteed to be a null terminator. Okay, but at this part of the logic, you're expecting a digit, right? The null character is not a digit. That will terminate the loop looking for additional digits. When you get out of that loop, then you have concluded that I have parsed the exponent part already. And then you have your local variable. Remember, the exponent is negative, and the value of the exponent is 5. Is that okay? So using the local variables, you will say, okay, what is stated in the string is -5 as a value. But on top of this -5, I'm adding this -5 to whatever EXP10 already has. What is the value of EXP10 at this point? -1, very good. So we are adding -5 to -1, which will give us -6. And you store that -6 into EXP10. So in the end, what you will end up with would be something like this. Okay, so you end up with P dot signed is some kind of non-zero value. Okay, best to describe it like this. Okay, it is not 0. Mantissa should be 27 exactly. P.exp10 has to be -6 in this case. So my script is going to check these things at label L1 to make sure that you indeed parse the number correctly. That's one test case. So I'm going to throw many test cases at your program and make sure that your program works on all of those test cases. Yes?
Will all of the information be valid? Like you won't have like double decimal points or actual characters?
Yes, that was something that we talked a little bit earlier. The input is always guaranteed to match the regular expression. Yep.
Are you creating to use any library functions such as string.h, anything in there, such as like str.
Ah, good question. It is also answered in the homework description. Okay, so do not modify the main function in any way that when you submit your program. You cannot use any parsing function in the standard C library. Otherwise, you can use ATOL, to do some of the work. ATOF works even better. ASCII to float, right? Yep, boom, done. So no, you cannot use existing parsing functions in C. So if you are going to use any function, you might want to ask me first. Okay? There are certain string functions. Most of the string functions that start with str probably is okay because I really don't think those are going to help. Okay?
They're okay because they won't help you anyways.
Well, anything that like substring. STR substring.
Yeah, str looks for substrings, but that's not going to be useful because you don't know exactly what you're looking for. And string functions, there are no regular expression, handling capability in the string family of functions. So they're not going to be very helpful. So if you want to know whether a particular C standard library function can be used, you might want to ask me first. Okay, so don't make an assumption. Doing everything using your own code is not that big of a deal. Okay, it really is not. Question?
Could we essentially just recreate the standard library functions?
That's basically what we're doing. Yes,
Yeah.
we're
Yes.
recreating, ATOF, in a way.
Don't look up the code.
Open source, right? It's part of the GCC, C library, so it is open source, and I will probably recognize that code when I see it in the submission. It's like, how come this function that is only supposed to be 20 lines long is now 2,000 lines long? It's like, and it's handling all the other options that I did not mention at all. Feature creep. Okay, very good. It's more like feature leap this time. In this case, off a cliff. People think of leaping as usually a good thing. It depends on what you're leaping into. What is?
Would we be able to use it for reference stuff? Would we be able to use it for reference stuff? To see how they do it, to see how that might feel, how we might be able to change that to work here. So this we're creating it anyways, but
I would try to figure out it by yourself first, because that's part of the homework is, okay, I want you guys to figure it out.
Okay.
Just do it by hand, okay? Do it by hand first.
Okay.
And use the technique that I just talked about. Look at it one character at a time, and then maintain your variables on the side, and see how you can say, oh, okay, this is the end of this section, moving on to the next one. Yep.
It probably wouldn't be very helpful either to look at their implementation.
Yeah.
It'd be like looking at the entire McDonald's business model to figure out how to deep-fryer works. It's not going to help you very much. It's somewhere in there.
Sort of like that, yes.
I just wanted to ask for clarity.
Well, but some people may be curious. Okay, so I'm going to show you how I will grade your program, okay, so that you know what to expect. Okay, so I'm going to run this program. So the way I compile this program, which is something that you might want to take note of, is GCC with a -G to include debug information. This is how the debugger can refer to the lines of source code, the labels, and the variable names and stuff like that. -O, this specifies the name of the executable. I just name it the same, it doesn't have to be. And then we have the name of the source file. In this case, there's only one, okay? And personally, I would also include -uppercase WALL, which is warn all. Okay, so it will turn on all the warning messages in case, because the compiler is actually exceptionally good at catching little things. Like you have variables that you have not used. Okay, you have variables that you refer to, but it has no initial value. So the compiler is actually pretty good at catching those mistakes that can cost you big time, when you're trying to debug your program. So in this case, it only has one single warning where the W label is defined but not referred to, but that's because I'm going to use it in GDB in my own script to grade your homework. Okay. So the next thing we want to do is to run this program inside GDB. So I'm going to use GDB parse sci, just like that. And in my script, I'm going to do everything that I type in the script. So I'm going to put a breakpoint at the label L1 in main. This is how you specify a particular label in a particular function. Okay. And the great thing about this is it's not dependent on line numbers anymore. So you can have all the code ahead of this, changing all the line numbers. It's okay. I'm not relying on line numbers. And when you run the program, you start with the R, okay, and you give it a parameter. So let's say we wanted to parse 3.07 e minus 36. Okay. Okay. Press the Enter key, and because of the breakpoint, I'm now stopping right before the return, which means P as a structure should have the proper values already. So what my script is going to do is to check each one explicitly and compare that to the expected answer. So I would print p.sign. It should be 0 in this case because this is a non-negative number. Okay, that's cool. p.mantissa is going to be wrong because I did not actually do any processing. So this would be wrong because it is supposed to be 307. Okay. This is wrong, but that's okay because that's just the initial. It's because of the initialization, and then exp10 exponent 10 is also 0 just because this is how I initialize. But in your program, it should be negative 38 because negative 36 is what is stated. But because I'm shifting the decimal point twice, each time I shift, I have to decrement the exponent by 1. So that means the negative 36 should now be negative 38. Is that okay? So my script will basically do all of these things automatically, and if it is wrong, then your program would have failed one of the test cases that I throw at your program. Is that okay? So it also means you can automate the test as well, because now you can say just everything that you type in GDB, you can put all of those into a file, and then have GDB to run that script by itself. So that can automate your testing of your own code. So if you can think of really tricky cases, add to that script so that you can have one single test file, one single test script to check everything that you can think of without having to retype everything every single time you make a change to the program. Do you have to have your own test script? No, I'm just giving you a tool to help you with improving the efficiency when you're writing this program. Is that okay? Now obviously this only works well when you're using the command line version of GDB, but every time you install code blocks, GDB is installed, GCC is already installed as well. So the only question is how do you get to GDB and run it manually instead of having code blocks to run it in the back end. Is that okay? All right. So getting back to ARGV. So ARGV0 is the name of the executable itself. ARGV1 is the first thing that is after the command itself, and then you have ARGV2 if you have more items, and so on. So it's a pretty useful construct, but I'm only using it, for this homework assignment, so that this is easier for me to test your program with different test cases. Are we doing okay so far with this discussion here? Okay. So when you go back to the homework description, it is kind of long because I'm also giving you some tips of how to compile. Okay, GCC to compile, GDB to debug. Inside GDB, this is how you set up a breakpoint at the label. This is how you run the program. I mean, this is all the stuff that we have talked about. You can also print P instead of print P dot something. So when it will just list all the members. So you can use one single print. If you're doing it visually, instead of using the script, this is the best way to do it because it will show all the members at the same time. But on the other hand, if you're trying to automate this, then you want to compare each one with the expected value. Okay. If you want to set up an arbitrary breakpoint on a certain line, you can say B and then followed by the line number. So in this case, it will set up a breakpoint on line 24 or the first line after line 24 that corresponds to code. Okay, so if line 24 is comment, okay, then it won't get a breakpoint, but the next line that actually has code that is breakable will get a breakpoint. When you are at a breakpoint, when you run the program and you're at a breakpoint, you can continue the execution using one of three usual ways. S is single step. Single step will only execute one line of code at a time. If that line turns out to be a function call, it will stop on the first line of the function. So single stepping steps into functions. If you do not want it to single step into functions, you use N, which stands for next. In other words, if the breakpoint is on the line where it is calling a function, and you say, I think this function is going to work fine. I don't need to step into the function. Then you type N and then enter. That will step over the function, which means it executes the function without stopping in the function. Okay. If you say, oh, I just want the program to continue executing until the next breakpoint, then you use C for continue. Is that okay? All right. Okay. Moving on. Some of you will have a program that will be stuck in an infinite loop. Okay. Well, the good thing about GDB is you can type Control-C, but Control-C doesn't terminate the program. It only pauses the program inside the debugger, which means after you type Control-C, GDB will tell you which line you're on. Whatever line you're on is a part of the infinite loop. Okay, that is really helpful information. And at that point, you can single step, you can next, you can continue, you can examine the variables using print. Okay, in other words, this is much better than having a cout in a program that just keeps continuously spewing out stuff when you're in the infinite loop. Because that doesn't tell you, well, it does tell you which loop you're in, because of the location of the cout, you know that cout is a part of the loop, but it doesn't give you any ability to say, oh, I want to check what is this variable. What is PTR pointing to? Where am I at in the parsing logic? It doesn't let you do any of that if you just use the cout for debugging. But in a debugger, it gives you information. It gives you a lot more information than the cout. Okay? So are we okay so far with the basic commands of using GDB? Most of those you can do in code blocks as well. I don't know the shortcut keys at all because I don't use code blocks at all.
You gave us instruction. You gave us a link for instruction.
I gave you the instruction to supply the number when you run the program, because you need that trick in order to run the program with argv1 populated.
There's no C in order.
Huh?
Because there's no standard.
Right, because your argument is not coming in through cin, it is coming in through the arguments of the command line. So that instruction only applies to, okay, how do I specify 3.23, as the argument? So it only applies to that. Yep. In the long run, I think the command line versions, the command line way of doing things is more efficient, but it will take you time to build up to that competency, to be effective. So it's up to you to decide, okay, I just want to stick with code blocks because I can get it working code blocks, or do I want to switch to GCC and GDB, all the command line tools? It's entirely up to you. Is that okay? All right. Sorry?
Oh, it depends on how much of a hacker we feel like that day.
Yep, and also how much homework are you getting from your other classes? Okay. Yep. So I do understand that stuff. Okay, what to turn in is really just the source file. There's nothing else. Just turn in the source file, upload it, and that's your submission. You have 1 week to work on this, so that means it's due next Wednesday at 10:30. Do we have any questions about the homework itself? Okay, during the lab session today, you are going to work on this. Okay, if you have any questions to ask, the lab time would be a good time to ask, because you can ask me about specific cases. What about this? What about this? Or what do you mean by that? And so on. Okay. But this is only the first part of a bigger homework assignment, because the bigger homework assignment is to use the output or the result of this particular program in order to come up with the actual binary representation of a double. So this is only the first step. So the second half is all math. The first half is basically mostly parsing. Okay, mostly the logic of scanning through an array of characters and determining, oh, I'm done with the numerical part. Now I'm expecting an optional E. If I don't see a E, I'm all done. If I do see a E, then I'm expecting to see an optional sign followed by at least one digit. So that's mostly just kind of linear logic, with some loops in it. The second half of the homework assignment, which is going to be due maybe, which is going to be assigned next week, is to convert the base 10 scientific notation to the double, which is binary. Okay? So let's take a look at this. So regardless of whether M10 is something that is like 2.3 or whether it's represented as 23, it doesn't matter. Okay, it is just a quantity that you will multiply to 10 to the power of E10, okay, exp10 in your program, and this entire thing is the value represented in scientific notation in base 10. Okay. But what we want to do is to convert everything to base 2, so that we'll have a different mantissa M2 that is multiplied to a power of 2, which is 2 to the power of E2. This is our objective. We want to convert from this to this. Is that okay? Now once we have E2 and also M2, the rest is pretty easy. Okay, the rest is just normalizing the mantissa, adjusting E2 because it is already offset by 1023. That's easy stuff. Okay, so our focus is really how do we go from M10 times 10 to the power of E10 to M2 times 2 to the power of E2. That is the main focus, because that's going to be the difficult part. So in the conversion process, the whole idea is, well, okay, this is already done in your homework assignment. In other words, if the input is 2.67, I want it to be represented as 267 times 10 to the power of -2, which is something that we talked about at the beginning of today's lecture. So that part is already done. I'm not going to talk about that again. And this part here, you don't have to worry about, because I'm making sure that whatever number I give you to process, the mantissa is not going to be so big that it cannot be represented by a 64-bit unsigned integer. So that part is done already. Okay, so no big deal. This is just going through some quick math to figure out, okay, if we have a 64-bit unsigned integer, how many base 10 digits is that corresponding to? So it's a quick way to do the estimate. 64-bit, means that the largest unsigned value is going to be 2 to the power of 64, the whole thing minus 1, right? So this is, but I break it up into 16, which accounts for 4, okay, 2 to the power 4, and then the other 60 is grouped here. But 2 to the power of 60 is 2 to the power of 10, the whole thing to the power of 6, right? In computer science, one really quick trick that we use is to look at 2 to the power of 10, which is 1024 in base 10, and just say that, hey, that's pretty close to 1000. So we use approximation, right? So that's why I can look at how many 2 to the power of 10s we have, and just kind of replace this with 1000. So that's how we end up with 18 digits in base 10. But because 16 itself is also greater than 10, that accounts for another base 10 digit. That's why I came up with the estimate of 19 decimal digits will exhaust what you can represent using 64-bit as an unsigned number. I'm not going to give you a 19-digit number to process because that takes a lot of typing on my part, even if it is read in a string. So I'm going to give you something like 4 or 5 digits or something like that. All right. So the difficult part is getting rid of the exponent of base 10. So when you're making the transition, the value that we are representing doesn't change, but the way it is represented internally is in flux. In other words, all of these things will be changing in the process of converting from base 10 scientific notation to the double internal representation. Okay, so the components will still have a mantissa, but this time the mantissa does not have a suffix. It doesn't have a subscript because it is just a mantissa. It is a mixture of base 2 and base 10. And that's why there's no subscript here. It started off as M10, okay? In other words, M is initialized by M10, but it doesn't stay, as a base 10 much longer. But we also have 2 exponents, okay? When we're in transition, we have 2 exponents. We have E2 being the exponent of 2, and then we have E10 being the exponent of 10. And the idea is this is non-zero to begin with. This is 0 to begin with when we start the process. So the idea is to make this one 0 eventually. If it is negative to begin with, we want to increment it until it is 0. If it is positive to begin with, we want to decrement it until it is 0. Is that okay? But in the process of changing E10, we will have to make some changes to M. And as a result, we might need to do something to E2 to compensate for that. So E2 starts with a value of 0, but in the process, it will get changed. Okay, so if E10 is negative, then E2 will start to become negative as E10 approaches 0. If E10 is positive to begin with, then E10 will decrement to 0 eventually, but E2 will increment in the process to some non-negative value. Is that okay? So far so good? Okay. So this is the general strategy of how we're going to do the conversion. But in the conversion, it is unavoidable that we will need integer division. Okay, integer division is, it's not a big deal. We know that, right? But one thing about integer division is it will lose something. What is 23 as an integer divided by 10 as an integer? 2. It's 2, not 2.3. Where is that 0.3? Truncated, lost, gone. Okay? So, but when you look at 0.3 out of 2, what is the percentage? Just give me a rough percentage. 15%? Yeah. So 15% of error is a big deal. Okay? We don't want to have that kind of imprecision in our division. What about 2003 divided by 10? Is 200. What about the error? The error is still 0.3, right? The absolute value of the error is 0.3, but it's 0.3 out of 2000 instead of 0.3 out of 2. So the ratio of the error is not the same anymore. In other words, exactly. So what we want to do is to maximize the numerator or the dividend when we're performing division in order to minimize the error.
So there will always be error when we do this transformation?
Oh yeah. Well, not always, but in most cases there will be errors. Yeah, in most cases there will be errors, but we want to minimize the error. But the only way to minimize the error is to maximize the dividend, which is the number that is being divided. Okay. Do you guys know the terms dividend, divisor, remainder, and quotient? Okay, we can do that. Okay, so when you have a division, okay, so we have dividend divided by divisor equals to the quotient with a remainder after that. So that's the complete form of a division. Okay. Right, but you can also look at this in a different way. The other way to look at this is the dividend dividend is quotient times divisor plus remainder. I know you guys know the priority of operators already, but doesn't hurt to emphasize. Is that okay? So is that kind of helping you guys remind you, what these terms are? Okay, all right. So once we know these terms, we go back to the discussion here. Okay, so the first part here is basically saying, if you give me a numerator and a denominator, or you can look at these as the dividend versus the divisor, I can always write n as some kind of product of the divisor plus a remainder. Okay, the remainder may be 0. Okay, that's fine. The quotient itself may be 0. That's fine too. But there's always a way to re-express n as a natural number as a product plus a remainder. So if you plug this in to n, then we end up with dq plus r divided by d, which will give you an integer of q, or natural number of q, plus r divided by d. The r divided by d part is going to be the fractional part, because r is guaranteed to be less than d. The remainder of a division is always less than the divisor. Okay? And this is the part that you're going to lose in integer division, because integer division does the truncation, which gets rid of the fractional part. Is that okay? And that's the part that we want to minimize. So in order to minimize the ratio of r versus n, we want to maximize n. Okay, so that's one thing that we have to deal with. The second thing we have to deal with is when we are truncating, which is always going to happen. Every time we truncate, we are losing something. The value is getting smaller. When you compare 2.3 versus 2, it's smaller. 2.2 is smaller than 2.3. When you divide 23 by 10, the integer result of the division is smaller than what it is supposed to be. When you look at 2003 divided by 10, even though the error is less, but it is also smaller than what it is supposed to be. When you look at 2 million divided by 2,000,003 divided by 10, it has the same property. Even though the error is now very small, but it is always, the value, the result is always smaller than what it is supposed to be. So we have a bias. This is called a bias because every time we err on one side, never the other side. Is that okay? It's a bad thing. Okay, we don't want to have a bias. It's okay to have errors, but you don't want the error to be a bias. Okay, so how do we deal with the bias thing? Well, we use rounding. So as it turns out, when you're rounding something, it is really the same thing as adding 0.5 first and then do the truncation for non-negative values. Okay? Well, let's think of a few cases. Let's think about 0.2. Okay? What is round 0.2? Now, you already know round 0.2 is supposed to be 0, but I want to check whether the equation works or not. So we want to look at this as truncation of 0.2 plus 0.5, which is the truncation of 0.7. When you truncate 0.7, you get 0. That works. 0.5 is a boundary case, which is always good to test. It is supposed to be 1, because 0.5 is when you round up to 1. Okay? But when we use our method, it becomes the truncation of 0.5, which comes from the original 0.5 here, plus 0.5, which is a part of the method that we are using. It becomes the truncation of 1, which is 1. Cool, that works too. Okay, so that means this method of adding 0.5 to whatever you're truncating and then do the whatever you're rounding and then do the truncation works. Is that okay? But if you know what you're rounding is the result of a division, then you can do a little bit more. You can actually do some trick, like what I'm doing here. So what you do is you say, oh, I know that I'm rounding the result of a division. So what about this? I can just add 0.5 of the divisor to the original dividend before I actually do the division. And then once I do the division, I do the truncation instead of the rounding, because the rounding is already integrated into the overall dividend, which is n plus 0.5d in this case. So, is that okay? Now, in your program, you don't need to do the explicit floor because integer division automatically truncates. So all you have to do is to add 0.5 or half of what your divisor is to the dividend, and then do the usual integer division. It is automatically rounded. Now the good thing, it's really nice that d in our case is either 2 or 10. Both of those are multiples of 2, which means 0.5d is either 1 when d is 2, or it is 5 when d is 10. So it works out pretty good. All right. So with these two things in mind, then we have two possible cases where in one case exp10 is less than 0 to begin with, it's negative to begin with. So what do we have to do to bring it to 0? We have to increment it to 0. How do you increment exponent of 10 to 0? You have to somehow adjust for that, right? Every time you increment the exponent of 10, you are implicitly multiplying the value by 10. How do I compensate for that multiplication by 10? Hey, we can divide the mantissa by 10. Is that working okay? So incrementing the exponent of 10 can be compensated by dividing the mantissa by 10. Okay? But we want to maximize the precision, right? Which means we want the mantissa to be as big as possible before we divide it by 10. How do we make it as big as possible? Well, we use a loop here. This doesn't look like a loop. It is a loop. Because the word as long as is the same thing as while. Okay? As long as is the same thing as while. What is the condition in the while? M is less than or equal to the largest numerator value, or dividend value, plus 5 divided by 2. Okay? How do we get that? So one thing that you also want to consider doing in your program. In fact, I would do this myself. Okay, the first thing when you get the template program, I would do this. I would do a pound include standard int.h. Okay, this one single header file will give you a lot of really cool things, because one thing you can do to make sure your mantissa 10 is a 64-bit unsigned number is to change this one to uint64_t. This is a type def in the header to guarantee that you will have a 64-bit unsigned integer. There's no doubt anymore whether mantissa 10 is 64-bit or 32-bit, regardless of the compiler. If you compile this using a i386 machine, it would be 64-bit wide. If you compile this using a 64-bit processor, it will still be 64-bit wide. Okay? But along with this comes other advantages. So let me see if I can do this. Nope. Nope. Okay. You can look it up online. Okay, just look up stdint.h online, and it will define. Okay, it will define those maximum and minimum values for all the types. So that makes it easy for you to figure out, okay, when do we get out of the loop? When m is no longer less than or equal to this value, it's time to get out. Because we have already maximized everything. Yep. So what do we do in the loop? For each iteration, you would multiply m to itself by 2. So you're doubling m. And you're also decrementing E2 by 1. E2 would be initialized to 0 before this whole process begins, okay? But every time you go through each iteration of this loop, you have to decrement E2 by 1 because you're doubling the mantissa. So you have to somehow find a way to have it, but this time we're using exponent to do it. And once you're done with this step here, then you will perform this step here, which means you're adding 5 to m, to do the rounding and then divide the whole thing by 10. The floor is implicit already in an integer division, so there's no need to actually perform the floor function. But mathematically speaking, I have to mention this is the floor so that we lose the fractional part. Is that okay? And you increment E10 by 1 because you have just divided the mantissa by 10. So you can now increment E10 by 1 so that the represented value will still be about the same. It's not the same anymore because we have some rounding and some other issues, but it will be pretty close. Is that okay? So these two steps would occur in sequence just like this. Okay, you maximize M and then you do the division. You keep doing this in a loop, and this outer loop that is not actually explicitly represented here has a condition of, as long as E10 is less than 0, keep doing this. Because what we do is we are incrementing E10 by 1 each time we go through the outer loop. So eventually your E10 will go from the negative value to 0, then you can exit. Is that okay? What about the other case? What if E10 begins with a value that is more than 0? Okay? Well, we do the opposite then. So if E10 is more than 0 to begin with, we want to decrement it. But in order to decrement E10, it means you have to multiply mantissa by 10. Does that make any sense? Okay. So what we do in this case is we also want to maximize the we want to make room first. Okay, so this is slightly different. So we are trying to make room to make sure that there is enough space to divide, to multiply by 10. So that means we have another loop here. We say as long as M is not less than the largest integer divided by 10, we perform these steps. So what we do is we keep dividing by 2. In other words, this is assuming that M is a really big number. If you multiply M by 10, it is going to exceed the largest value that you can represent using 64 bits. Okay? Because the next step is going to do that. So we got to make sure there's room to do the multiplication by 10. So this is the loop to make sure that you have room for that multiplication by 10. How do we make room? You keep dividing it by 2 and adjust E2 so that we are still using approximately the same value until you get that room. Is that okay? Sort of? Okay, so once you have made room for the multiplication by 10, then you just go ahead and multiply M, the mantissa, by 10, store it back to itself, and then you decrement E10 by 1, because by multiplying the mantissa by 10, you have to adjust your exponent of 10 by decreasing it by 1, so that the value represented will still be about the same. Is that okay? So you perform the loop, this step, the loop, this step. You keep doing this until E10 is no longer greater than 10. Because each time you're decrementing E10 by 1, and it starts with a positive value, so it goes from positive, 1 less than that, 1 less than that, until it gets to 0, then you get out of the loop. Are we okay with the general strategy of converting or getting rid of E10? Okay? All right, so we are running out of time today. It's already 11:49, and the next section kind of takes a little bit longer to explain than what I can do in a minute. So I'm going to stop the lecture at this point. And I forgot to take roll today.
Got your
Well, we can. I'll do it next time. Or I'll just drop everyone who has at least one absence. Yep. Sorry.
Can I vote for not doing that next time?
Motion. There's someone proposed a motion. Is anyone going to second it?
I will second.
Okay.
I'm not
Alrighty. So I'm going to move. I'll go to the lab. If you want to work on the homework assignment, we'll go to the lab. Oh, I got to give you the solution of the homework, the subtractor homework, using multi-bit gates. Okay, so that's what I'll do over at the lab. If you don't really care about that, that's okay. But that's what I'll be doing at the lab for the first part, and then the second part is just for you guys to work on the homework.
Change the label. Yeah, okay.
Yeah, I made sure of that.
It took me